In the galvanic cell, the reaction happens spontaneously. When the electrolytic cell, the reaction does not happen spontaneously. So you need an external source to reverse the current. So basically, when you discharge, your cell is galvanic. When you recharge, your cell becomes electrolytic. Hello everyone, my name is Sara Spirigoi and I'm a PhD candidate in electrochemistry. Before I go deeper into the galvanic and the electrolytic cell, there are some things that you need to understand before you can understand those. I want to start first with what is electrochemistry. And if you Google it, or ChatGPT now, I guess, what you find is a very long and complicated definition. What I want you to remember in a simple way is that electrochemistry is the science of turning chemistry into electricity and vice versa. So electricity into chemistry. That's it. Now, I'm not like a huge fan of definitions, but I think that if you understand what is an electrochemical system, you basically understand half of electrochemistry, or at least what electrochemistry is really about. So an electrochemical system is made by two things only: an electronic conductor and an anionic conductor. That's it. The electronic conductor is a material that can conduct only electrons, while the ionic conductor is a material that can conduct only ions. So the ionic conductor cannot conduct electrons, and vice versa, the electronic conductor cannot conduct ions. So in this case, this is the simplest electrochemical system you will find, which is a piece of metal immersed in a liquid, like usually water. The electronic conductor is called the electrode, while the ionic conductor is called the electrolyte. But the ionic conductor also has inside the ions. So the ions plus the solvent is the electrolyte. So this device on its own does not produce any energy. What happens here is just corrosion at the surface of the metal. And I'm going to cover corrosion in another video. Right now, I want you to understand one important thing. So how can we produce energy? Let's take two identical pieces of metal and immerse them in the same electrolyte. What happens now is nothing. So you're not gonna see any energy coming out. So you're not gonna see the light bulb lighting up. Why? Because the electrons inside both of this material have the same energy. So in order to get energy out of the device, we need to have two materials that have electrons that have a different energy levels. So if you take another material which electrons have a different energy level, then you will see the bulb lighting up. And in this case, you will have energy. Okay, but why do you have energy? What's going on here? So what happens is that the electrons from the highest energy level will flow spontaneously to the lower energy level. And in this case, the electrons at the highest energy level are actually at the lowest potential, while the electrons at the lowest energy level are at the highest potential. I know this sounds very confusing, but I'm going to explain the concept of potential in my next video. So the issue is that the electron flow does not correspond to the current direction. The direction of the current is actually the opposite of the electron's flow. Why is that? Is that because when they decided the conventional current, the direction, they didn't know that the current was made by electrons. So they took the assumption that the current was just made by positive charges. And they never changed it ever since. Anyway, what you need to know is that the electron flow is not the conventional current. But regardless of the nomenclature, so we get energy only if we have two materials that have electrons at different energy levels. So let's try to build a device. Let's take the zinc and copper. Okay, these are two materials that have electrons that have different energies. And let's connect them through a wire that, let's say, does not react with the metals themselves. What happens in this case is that we have a connection between the electrodes. So the materials actually feel each other. So the electrons feel that there are other electrons on the other side of the cable that have less energy and they want to flow there. But what happens is that the moment the electrons, they leave the metal, because the electrons in this case, they want to go from the zinc to the copper. What happens now is that when we have an electron that is leaving the metal, we have automatically a positive charge that is going to stay on the metal. This is going to create an electric field that is going to counterbalance, that is going to block the electron flow. And the same thing is going to happen here. You're going to have electrons in the wire that will try to go into the copper, but then the electric field is going to block them. So That's why nothing happens. But you must be thinking, yeah, okay, but you said at the beginning that the electrochemical system has also an ionic conductor. And you're very right. So let's put an ionic conductor right now. You put an ionic conductor, you immerse your 2 electrodes inside, let's say, water like distilled water. And nothing happens again. And you're like, what? Like, I put the ionic conductor. What's going on? And what's going on in this case is the same basically thing. So you have the zinc that is getting oxidized, so it's releasing electrons inside the circuit, and also the ions of the zinc are released inside the solution. But the problem is that on the other side, on the copper, the electrons want to go inside, but you have nothing that can go on and take those electrons. So you say, okay, let's put copper ions like copper sulfate inside the solution, okay? And now we have an electrolyte. And what happens now is that, boom, your light lights up, finally. But just for a couple of seconds or minutes, then it goes off again. And you're like, what? Like, what happened? Like, it was on. And then it went off on its own. Like, what's going on here? And what's going on here is that since zinc has the electrons that have a high energy level compared to the copper one, what happens is that the zinc releases, like gives the electrons right away to the copper ions inside the solution. So you're gonna have the copper that is going to plate on the surface of the zinc, and then the zinc ions are going to be released inside the solution. So the problem here is that not only the copper is going to passivate completely the surface, blocking completely the reaction, but also this system is bypassing completely the external circuit. And that's why you have a bit of light before the surface goes completely passivated, but it's not going to last longer. All right, so you think, let's separate the electrodes and put them inside their own solution. Let's do that. So you take 2 different containers, you immerse the electrodes inside their own solution, and you wait, and nothing happens. Why? Nothing happens because you just open the circuit. So there is no solution here that can close the circuit. It's open. And this is why we need ions to complete the circuit. So let's take the solution and put like negative charges on the left and positive charges on the right. And we put ions inside our solution. What happens is that now the positive ions are going to be closer to the negative one, and the negative one are going to be closer to the positive one to compensate and give the whole system the electroneutrality. But let's say that now you take some of the charges and you put them on the other side, and then some of the others of the positive one you put them where they are the negative ones. What do you think will happen to the ions? What happens here is that the positive are going to repel each other, and the negative also are going to repel each other. So you have a redistribution of the ions inside. It is the movement of the ions that allows the electroneutrality to happen. And it's the electroneutrality that allows the electric field that counterbalances the movement to just disappear. Because if you don't have the ions inside, the electric field that is generated because of the charge separation is going to grow so strong that it's going to block the charges from moving again. And so it's going to block completely the reaction. So if you want the reaction to go on, you need the ions to move and maintain the electroneutrality. And you can do that even with indifferent separators. So let's say we have our solution and then another solution. And then we have another container that is between our solutions. Okay, and both of them can conduct ions. So let's put, for example, potassium chloride inside. And we put a ton of it. So why do we choose potassium chloride in this case? Because both potassium and chloride, they have the same ionic mobility. So they flow at the same rate. And this means they're going to move to maintain electroneutrality without causing a main charge imbalance. And since potassium chloride is salt, and this is kind of a bridge, this is called salt bridge. Brilliant. So we're going to have our own copper, let's say here. And what happens is that the salt inside the bridge is going to move. So the ions inside the bridge are going to move to keep the electroneutrality, okay? And we don't care if they go out, okay? The important thing is that we have so much that the copper inside our own solutions don't go back in and they don't cross and go to the other solution. So you put your beautiful salt bridge between the solutions and ta-da, you're going to have the light bulb going on again. Beautiful. And this is what we call a galvanic cell, because we have the reaction that is happening spontaneously. So what happens here, spontaneously, the zinc is getting oxidized, so it's losing electrons. It's going to release them to this external circuit, and it's going to release zinc ions inside the solution. On the other side, the copper is going to take in electrons, and the copper ions inside the solution are going to take those electrons and electroplate on the electrode. So what happens is that you see the zinc gets consumed and the copper grows. Okay, and all of this happens spontaneously. You just leave that, no wire, nothing around it. And you're going to see it inside the salt bridge, that since we're going to have less positive charges because they're going to take electrons, an electroplate here, you're going to have more, let's say, negative charges. So the potassium ions are going to flow inside here and are going to counterbalance this thing. And the same here happens. Since we have zinc ions released in the solution, the chloride ions is going to move and is going to keep electron neutrality. And this is why you're going to see this cell going on until whether the whole zinc is consumed or the whole copper inside the solution is consumed. Okay, but now I want to recharge it, and I want to see that again. So I'm going to plug in a galvanostat that is going to impose a current. So I have an external source that is going to force the current to go to the opposite direction. And then you're going to see, bubbles going on inside your solution. And you're going to think, what's going on? Right now, what's happening is that you're forcing the current to go in the opposite direction. So the electrons are going out of the copper, and the copper ions are released inside the solution. While on the zinc side, electrons are going towards the zinc, but you don't have zinc ions in the solution that are going to take these electrons. So the system is going to find whatever can take those electrons to make the reaction go on, because we have an external source. So before, the reaction was stopping because the device was there on its own. Right now, we are forcing it. So the system has to give those electrons to something, and it gives them to water. And that's why you see the bubbles. So the bubbles are actually hydrogen evolving. So what you do is that you put also zinc ions inside the solution. And now you have your complete Daniell cell that can both discharge, galvanic cell, and both being recharged, electrolytic cell. Now, you probably noticed that I didn't use the name of the electrodes. I didn't use anode, I didn't use the name cathode, I didn't use positive electrode, I didn't use negative electrode. The reason is I wanted to keep this for now, for this explanation, because there are actually two ways of naming them. And this is one of the most confusing things in electrochemistry. I remember, when I was a student, when I was studying electrochemistry, I was going crazy because I kept seeing two definitions that were opposite. And I thought I was stupid. I thought, what's going, one says one thing, the other one says another thing. And this is where I figure out that there are actually two nomenclatures. So I'm going to explain them right now. We have the chemical view and the engineering view. In the chemical view, you have the anode and the cathode that are fixed. The anode is always on the left, the cathode is always on the right. And what you have changing is the negative and the positive polarization. And the reason the chemical view is like this is because the chemical view sees the electrons always going towards the positive electrode, which makes sense. You have electrons that are going to be repelled, negative, negative. So they go away from the negative electrode and they go towards the positive electrode. So you have electrons that always go away from the negative electrode and always go towards the positive electrode. And this is during discharge. During recharge, the opposite happens. So the anode always stays to the left, the cathode always stays to the right. And what we do, we have an exchange of the negative and the positive polarities. So now the anode is positive and the cathode is negative. And as I said before, the electrons are negative. They go away from the negative electrode and they go towards the positive electrode. Now, the engineering view instead keeps the polarization the same. So it keeps the negative electrodes always on the left and the positive electrodes always on the right. And they don't change. The engineering view says that the electrons will always go away from the anode and they will always go towards the cathode. And the discharge is actually the same as the chemical view. It's the same. The confusion comes when we go to the charge of the engineering view. And in this case, so we have the negative electrode that stays on the left, the positive electrode that stays on the right. But the cathode and anode switched, because from the engineering view, you always have oxidation at the anode, always have reduction at the cathode. And you can see how this is very confusing, because if you talk about the anode from the chemical view, you're thinking about the positive electrode and you're thinking about the reduction. But if the person you're talking to is thinking through the engineering view and you talk about the anode, that person is going to think that you actually have an oxidation. So you're talking about two opposite things, literally. While the same thing happens, like if the engineer, for example, talks about the negative electrode, she's gonna have in mind that at the negative electrode you're gonna have the reductions, so the electrons going inside. And they're gonna say, okay, this is the cathode. But if she's talking to a chemist and the chemist here cathode, the chemist is gonna think that there is like an oxidation going on. So you can see how this is very confusing. My suggestion is to just ask which view they're actually using, if they're using the chemical view or they're using the engineering view. Just so you know, the UPAC is actually using the engineering view. So at the anode will always happen the oxidation, while at the cathode will always happen the reduction. And this is actually what it's called reduction oxidation. So how to remember this? There are several methods that you can use to remember, because it's not that one is correct and the other one is wrong, because it's not something like the object goes down because of gravity and then you say, no, the object goes up. It's not something like that. It's something that we chose arbitrarily, okay? So there's no right or wrong. As long as we understand what we're talking about, that we're talking about the chemical view or the engineering view, we're okay, all right? So since there is no reasoning behind it, I will always struggle to remember what is what. Like, where is the oxidation happening? Where is the reduction happening? There are several things that you can do. So whether you think about the vowels, so A and O, or the consonant, so CR. Or you can think about, if you like football, you can think about Cristiano Ronaldo, so you have CR. Or if you like cats, like I do, you can think about a red cat, because like it's cation, and here you have red. So you can think about a red cat. And with the AO, I have maybe one in mind that I don't think I can disclose here on YouTube, because they're gonna ban for sure the video. You can just become creative, and actually you just need to remember just one. You don't need to remember both. You just need one. All right. So in this video, I talk about the galvanic cell, the electrolytic cell. And I also introduced you to something that is confusing. Indeed, that is that electrons have a higher energy level when their potential is lower, while the electrons that have like a lower energy level, they have a potential that is higher. So that's why in my next video, I'm going to explain this much, much deeper. And I'm also going to explain the electropotential, cell potential voltage, standard hydrogen electrode, and standard electropotential, and much more. So if you don't want to miss the video, make sure you subscribe, and see you in the next video.